Hey guys, Mr. Betts here. Let's take a look at a couple examples of functions and determining where those functions are going to be increasing and decreasing. So if you remember, the first step to doing this is finding critical values for the function. So we're going to take the derivative, and so that's going to be 3x squared minus 3x. To find critical values, we want to know where that's either not defined, which there's not going to be any x values where that's not defined, or where the derivative is equal to 0. So we can factor, and we get critical values at x equals 0 and x equals 1. So now what we're going to do is we're going to organize our work in what's called a sign chart. And a sign chart is essentially just a number line. And on that number line, we're going to put the important values, in this case, the critical values. So we're going to put the 0 and the 1. And we call it a sign chart because we're going to be looking at the sign of, in particular, the derivative in this case. So I always want to make sure I label my sign charts with what it is we're trying to find the sign of. So sign meaning positive or negative. So these two critical values are the only two places where the derivative can change signs. So to the left of 0, the derivative is either always going to be positive or it's always going to be negative. Between 0 and 1, same thing. To the right of 1, same thing. So what we're going to do is we're going to just pick test numbers. So for the interval to the left of 0, I can pick any negative number. Sometimes if it's open going to the left, so it goes to negative infinity, I'll just pretend like it's just some really big negative number. But I can pick any negative number. And when I plug that into the derivative, remember we want to plug these into the derivative because we want to know the sign of the derivative, then we're going to get either a positive or negative value. So this work that I'm writing right here, I'm going to use -1. You don't have to do this on your paper. You just need to, you can do it mentally, but you need to do it for some value. We're going to have 3 times -1 squared minus 3 times -1. Notice that -1 squared is going to give us a positive. So this is a positive term, and a negative times negative is a positive. So I don't even need to know what the value is. I know this is going to be positive. It is a positive 6, but the important thing is that it is greater than 0. It's positive. So when we plug any negative number in, we are going to get a positive. If I plug in 1/2, remember I'm plugging into the derivative. So I want to know the sign of the derivative at this point. I plug in positive 1/2. I'm actually going to plug it into this. I like plugging into the factored form. Make sure that if you do this, that it's actually equal to the derivative. If those two are not equal, then we don't want to be doing this. So by plugging in the factored form, I can think of positives times negatives and what I'm going to get. So this is going to be 3 times negative, sorry, I keep saying -1/2, positive 1/2. And then I'm going to have 1/2 minus 1. So I have a positive 3, I have a positive 1/2, and 1/2 minus 1 is going to be a negative. So we have positive times negative is going to give us a negative. All right, and then I'm going to pick a value to the right of 1. Let's say it's 1,000. Okay, it really doesn't matter what it is. We're going to have 3 times 1,000 squared minus 3 times 1,000. And I said I'd do the factored form, so let's do that. 3 times 1,000 times 1,000 minus 1. So what's going to happen here is we have a positive, and then any number to the right of 1 that I plug in here, that's going to give that a positive also. So positive times positive times positive is positive. All right, so this sign chart is telling us that anywhere to the left of 0, the derivative's positive. But remember, if the derivative's positive, we want to know where the function's increasing or decreasing. That's going to tell us the function is increasing. So I'm going to start writing out my answer here. F of x is increasing on the interval. I'm going to use interval notation here. So -infinity to 0. I do want to include 0 because we're going to include the endpoint as long as the derivative is equal to 0 at that point, but it's adjacent to an open interval that is increasing. We're going to include it. And on the interval, so we also have positive derivatives here to the right of 1. So that's going to be, we're going to include 1. So from 1 to infinity. Remember, infinity is always an open interval. And the reason is there is no number at infinity, so we can't include infinity. Then we go to the decreasing part. So f of x is decreasing where the derivative is 0. So on the interval, and we should include the endpoints. So from 0 to 1. All right, so notice that we're saying that the function is increasing at 0 and the function's also decreasing at 0. But the important thing to keep in mind is when we include 0 in an interval like this, it's just saying that the value of the function at 0 is greater than the value of the function at any point to the left of 0. So it's not saying that at the point 0 is increasing. A function can't actually be increasing at a point. It's saying that that point is greater than any point to the left of it. And that's why we include it in the interval. Second example is really similar. So we're going to we want to figure out where the function is increasing and decreasing. So we want to find critical values by taking the derivative. And setting that derivative equal to 0. So I'm going to solve this by factoring. First, I'm going to factor out a 12x. That leaves us with x minus x squared minus 4x plus 4 equals 0. I want to make sure I bring down that equals 0. And then 12x, and then we have x minus 2, x minus 2 equals 0. So we have critical values at x equals 0, x equals 2, and we actually have a double root at 2, but we only include that once in our list. So now I'm going to make a sign chart. Again, I want to know the sign of the derivative, because where the derivative is positive, the function is going to be increasing, and where the derivative is negative, the function is going to be decreasing. So I'm going to include my 2 critical values on this, and I want to just test values on each region. So plugging in any negative number. Remember in the last example, I said I like using the factored form. So I'm going to be plugging into this form right here. So f prime of any negative number. I don't even care what the negative number is. It's just going to be a negative. So we're going to end up with 12 times some negative number. If we take a negative number and subtract 2, that's also going to be a negative number. And if we take a negative number and subtract 2, that's also negative. So if we have positive times negative times negative times negative, that's going to be negative. So on the interval from negative infinity to 0, we're going to have a decreasing function. Then from 0 to 2, easiest point to plug in there is 1. So we're going to have 12 times 1, which is positive, times negative 1, which is negative, negative 1. So that's going to give us a positive. Now you may be tempted at this point, because we saw this in the last example, to just say, okay, well, it's alternating. So it goes from positive, negative to positive and back and forth. But we want to be very careful here. This one's actually not going to do that. So if I plug in a number to the right of 2, some big number, let's say 100, this is going to be 12 times 100 times 98 times 98. So that's going to be positive, 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 and we get a positive derivative there also. So I want to point out why this happened, why it didn't alternate in this case, and it's because we had that double root here at 2. If we were actually to look at the graph of this derivative, if you go back to graphing polynomials, if we were to graph this, it's going to have zeros at 0 and 2. And a positive x cubed is going to be starting to the left and going up to the right. And it's going to have at most 2 turns. It's going to have 2 turns since it has 2 zeros here. But since it has a double root at 2, it goes through at 0, where it has a single root, and then it's going to bounce at 2. So we're going to get a function that looks something like this. So the derivative is negative to the left of 0, and it's positive everywhere to the right of 0 except at 2, but it bounces at 2 and stays positive. So If you have an idea of what the graph of the derivative is going to look like, it can really help make the sign chart a lot quicker. Now that we have that, we can determine where it's increasing and decreasing. So I'll say f of x is increasing on, so I'm going to include 0. And I'm not going to stop at 2 because it's increasing from 0 to 2, but it's also increasing from 2 to infinity. So 2 is included in both, so we can just say it's increasing on that whole interval from 0 to infinity. And then f of x is decreasing on the interval from negative infinity to 0, including 0.